Hello, welcome back to the stream. I'm Jun-chan, and we're back doing some Purescript. And we're still working on this graph library, algebraic graphs, ported from Haskell, and implementing a Comonad instance for it. And that led us through a whole bunch of rabbit holes and twists and turns and exciting moments. And we're now trying to implement the Comonad instance for one of our type of graph, which is the pointed graph. And this pointed graph is defined as basically kind of a wrapper around a normal graph, but where we keep track of where we have a certain vertex that we're pointing to. And so it means that if that vertex is actually connected or overlaid with other graphs, which are our algebraic operations here to combine graphs, we know that the pointed part is always on the left of these connectors. And so if we patient enough and we unpack that, we'll find our pointed graph. So that's a way to keep track of a specific vertex. And so that we have something to extract when we are implementing our Comonad instance. And the duplicates of it should allow us to put inside of our n to put another graph and have a pointed graph of pointed graphs. So that's what I try to do here. And however, what happened is that when I tried to run the tests, it didn't work. So I think we're supposed to be in a Nix shell here. I don't know why we're not Nix developing, by the way. Oh, okay, because we don't have a flake. That's why. And so Spago test. Should show us that yes, one of our attempt to represent laws with just a simple example just failed. So let's do a little bit of our regular housekeeping here. We're November 2nd, and we can copy the graph. Okay, here we go. And so fix failing test for extend extract. So let's see what's going on with our tests. So we first, so we're passing the extract function to to the extend higher order function. And we're doing that with a circuit that should point at A. So I suppose, first of all, we should just confirm. Okay, 1 second, I'll be right back. Okay, let's try again. So if we extract from that circuit overlaid with the path, I would expect that we get just A. So let's see whether that's the case or not. And then I think we'll try to extend like a small graph and see how that works out for us. Oh, that is not what I wanted to do. Okay, so we can extract from a pointed graph. Okay, so let's try to extend something smaller. Like let's try and extend just a p vertex of A and see how that goes. Actually, that's one to have, I think. Extract from a simple pointed graph a okay, complex is a bit of a lie here, but unexpected token, yes. We can maybe add one here. So we extract just fine. So let's extend and see where that takes us. So we can extend, I suppose let's extend ID, and we're going to need to take the adjacency list from that. And what's it going to be? Right, it should just be this. I suppose that's going to work because that looks like exactly what we're getting, in fact, out of our extend extract for more complex graph. Oh no, but I'm trying to do it with identity. So if I do it with identity, then here I should have a graph. Identity. Let's see what's the error we get. Is the type wrong here? From array. I mean, we know the type is wrong. I don't exactly know how to deal with what the representation is going to be. Let's maybe let's show that, and then try and see what what it looks like. I could not match, so I think I need to parenthesize. No show instance for data show pointed graph. Tuple pointed graph char. List pointed graph char. That makes some amount of sense. I do have an EQ instance, so I could actually be doing something like this. I think should equal p vertex of p vertex of A. But you do need, okay, maybe I can just derive or write a show instance. Do we have even a show instance for graph here? We don't, but I don't see why we shouldn't. So let's just write one. We're going to need one for graph, but you know what? It's due, long overdue. Read a superclass so that we can show the content. And I suppose this will be something like maybe P, or we can maybe do something cute like this to point at it, and then P connect NO or QP equals what? Yeah, equals show P, and we need the show instance on graph so that we can do show Q, and we can maybe, if this is connected, we can do something like that. And then if it's overlaid, we can do something like that. Maybe something like that. And we're going to miss a graph. Yes. Parenthesis here. And we missed the show instance on graph. So let's just write that one. And let's write it here. And we are not going to need to single out the vertex, and empty. It's just going to be just this. Well, maybe we'll write it. And we're talking about graphs and not pointed graphs. Okay, and then this now works. However, yes, and now, yeah, now this works, or I mean, at least we should equal graphs, which should be useful. And okay, so that works. So extend a simple pointed graph works. So let's try to extend a complex pointed graph and see whether we can make things work. I mean, most of this could be the extend for graph, actually, right? We could try and figure out whether extend for graphs is working correctly or not. And yeah, and I think then we can start simplifying most of that stuff, because what we want here is that this is equals to vertex 1. Is that right? Yes, it is. And then similarly here, if we put const a inside this complex thing, yeah, what we're saying is that we get back vertex a, but connected to itself though. So I think if we say connect, let's see, we could say connect and a list. Yeah, that's vertices. Connects would be one way from an array of edges. Yeah, we could do edges with a tuple, Or we could do edge. Yeah, we can do this actually, maybe. Yeah, that's an interesting thought. I want to find out. Actually, graph equality, I'm just realizing, is not going to be as simple as that. Because we're going to need to reduce things to canonical form. Right. So it's really vertex A. And we might be missing an edge at this point. Not much. Yeah, I'm not so sure about what I did there. Hold on. It should be this. Where is it not? Could not match graph char with char. That's should give the same error, right? No? Right. Oh, right. Yeah, so excellent. That's an example that our equality is bonkers. It doesn't work. It doesn't work unless we accept to pay a price for it, which is simple. And we can start with simple. But I think simple is not going to be enough, and we're going to need simplify. We're going to need to have some kind of canonical representation, which for some reason is not here, but it might be in the Alga library in Haskell. So first of all, we're not doing EQ, but maybe that's a product of us using sort of the test spec assertions here. Could we use something else? I mean, we don't have, it is useful to have that show instance, but yeah, I think maybe we can do EQ simplify. Okay, it's going to be simplify A and simplify B. Let's try this. Hey. So simplify doesn't work. Or something else going on. Well, let's play with simplify first and see whether it gives us something we expect. So let's test simplify on well, it doesn't have anything to do with the monad, graph unit, graph boolean, graph char, context of graph. Simplifying graphs. simplifies an empty graph. We need to import that. And that would be sure the empty graph, and I think we want it to be equals to empty, equal to empty. And let's try that. Simplifying graph, simplified empty graph, that works. And so what we would think is that simplifying an empty graph like that's, for instance, well, let's do something like vertex A. Let's do exactly what we were trying to do earlier. Edge, vertex A, vertex A. And we like to think, well, that doesn't simplify to vertex A, but we want it to at least not blow up. So edge, oh yeah, of course it's edge from A to A is what I mean here. Okay, yes, for this to type check. And yeah, so that sounds right to me, which is that this, yeah, so there's nothing really interesting to do here, except that if we then, let's say if we connect that to vertex A, then what we'd expect is that it would be edge A to A. And to be honest, here we should really be thinking about, that's exactly where we should be thinking about property testing. But let's not do that for now. So simplifies oh yeah, that works. Okay, simplifies a redundant self edge is what this is. Okay, so let's use connect again in a different direction, and this should still be equal a more redundant edge. Yeah, okay. So it seems that this simplify works. So let's see what would not work when I do EQ. I add simplify to EQ here. Maybe there shouldn't be an expectation that EQ does this. Maybe I should allow two different graphs to be different, and then I should just specifically simplify if I want to actually make things simplified. So what would that mean? That would mean that in extend graph, when I go there, then I'm sort of saying that if I simplify that, that we expect to have something like edge AA. So all of this overlaying of AAs should just collapse. Indeed it does. That's good. So that, well, I'm not sure whether that means that extend works. So let's do something else for extend. Right, I mean, that's where we do extend identity, isn't it? And then we try to put some graph inside. But it could be that we need to put edge AA inside here for it to work. No, not at all. Yeah, I need to create a simpler, to extend a simpler graph is what I need to do. So what am I going to extend? Well, I'm going to extend, yeah, edge AA. Actually, that's what. And we're missing parents here. And that seems to work. Yes. So what is that? It's extend. Yeah, it's basically it's the law, right? So Comonad law, extend, extract, blah. I mean, calling it a law is not what we should do. Example of, or yeah, one example of blah. So what's wrong with here then? Oh, so what am I doing? Hold on. This is extract identity, not extend extract. That's what's wrong. Okay. Extend graph, extend identity. Yeah, so that's definitely not an example of that. Extract. And we want it to be edge AA, and that's it. And we shall see. And this is what this is. This is just extends identity to a graph of graphs. And we don't have a Comonad on extend. So that's all fine. That's very true. On extend, on graph. We only have the extend. So we need to go to non-empty graph and try again. So it will be any.simplify. I don't know if I created one of those. Any edge AA, and also I think I haven't created a show instance for this. Okay, so let's bring in the kit. This should just work. And we just need to check whether we have a simplifier here. We do. Okay, so it should be fine. If I save. What? I don't have a Comonad instance for non-empty graphs? That's... Yeah, which one do I choose? Yeah, non-empty graph. And I don't have a reason to select any particular one. So I could just choose the first one, the arbitrary one, the last one that was added, or something like that, right? No reason I can't do that. I need to write it though, but that's fine. Where's it going to be? Comonad extend. Yeah, I mean, it's going to be a little bit like that. And this doesn't need to be here. And graph. And what? Which one do we take? Yeah, we take the one that's on the left until we meet one on the side, and then we're done. Won't that work? I think it could work. No. Control Comonad, class Comonad. And so in this case, yeah, well, in this case, it's actually trivial, so it should work. I mean, I don't know. Extend extract, it does work. I should also just test extract. So describe Comonad non-empty graph with let's say extract from simple non-empty graph, extract any dot vertex. That should be A indeed. And what else will we have? Yeah, so that would be interesting to find out what that's going to be. I think it's going to be A as well, just because it's the leftmost thing. But we need to test that. Oh, but then this won't exist in Comonad non-empty graph. So if I use this, yeah, because circuit takes a non-empty. Yeah, so it just works. There really is not much to it. I suppose I did create my graph with circuit. So let's try from another. Let's try something a little bit more suspect. Like we create a non-empty edge with A here. And let's say we an edge from A to, or an edge from B to A. And let's say that this should equal B. That we any connect this any with an any vertex next to graphs. Return the graph. Any edge. Okay, yes, that's the problem. And okay, that's where we start needing. I actually kind of want property test there, especially if we want to do things like simplify and I don't have QuickCheck here. Purescript. QuickCheck. Is there a Purescript like a hedgehog or not? Purescript hedgehog. There isn't. Okay, that's all fine. Test space QuickCheck. QuickCheck. And test QuickCheck. And then we spago install QuickCheck and spec QuickCheck. That's good. And we spago build. And then we say something like that. So yeah, I suppose that's fine. We do what? Well, we need to be able to generate some stuff. So there's a guide. It's a guide for Purescript spec. Fortunately, not linked anymore. Purescript QuickCheck. And the guide. Oh, there's a guide. Yes. Right. Text one argument property we'd like to test. Yeah, so let's write it how we'd like it. Let's do test-driven development of our tests. So I wanted to test simplify. And I had a simplify here. So it simplifies arbitrary graphs. And we do something like what was written in here. Yeah, which is just something like that. Okay. And that we get the G, and that maybe, yeah, we want that basically, for instance, connect of G and G. Actually, overlay, well, overlay of G and G should be G. And then we need an arbitrary instance for graphs, and we shall write it. We can remove all this. We can propel ourselves into the new, into Purescript 0 something. Okay, and instance RB A, arbitrary graph A. And I need some power apparently. Your power, your power. We'll need to import arbitrary. Test of QuickCheck.arbitrary. Import prelude as monad? That doesn't make any sense, does it? Monad dot. Do we have a monad dot? We have a monad dot. Okay, so it does make sense. Sorry for that. Test dot QuickCheck dot arbitrary. Doesn't this? Ah, yes, we need arbitrary. Which will do what? I'm trying to understand this arbitrary here. What will it, where does it come from? Boom. Do we need, yeah, we need, yeah, so gen is a generator, and depending on its type, I suppose it will give us what we need. So that's how this thing works, is that because of the map, arbitrary here has a type automatically of list that's inferred. And because of the blah divided by blah, I suppose it knows that it's some kind of int. Or num, and it generates some num, and then it divided by 1,000. Impressive. So how would I use that to my advantage? I suppose I could generate an arbitrary list of things and then do something from the list, right? I could generate I could do the reverse of that. Do I even have something like that? I thought I did. Maybe it's just oh, structural equality. Oh, interesting. Yeah, but that's EQ. That's exactly EQ, I believe. Yeah, I think that's probably equivalent, which we would need to test. We can add this. Equalities. Structural. It is structurally equal if it is equal. something like that, and then we'll QuickCheck. Yeah, I don't know that it needs to be a capital C there, actually. Oh yeah, it does. QuickCheck, given a graph G and a graph G prime. Can we have that? Or maybe we need to nest them. And a G and a graph H. G triple equal to H triple equals yeah, so we need to hide one of those because this I suppose if we import that as graph, then we can do graph dot triple equal here. So that's the graph dot triple equal and triple equals G equal H. It's an interesting one. Yeah, I think if we have our arbitrary instance, we should have a test for that. Okay, so back to generating an arbitrary instance. So I could do I could build it from vertices. That wouldn't be very arbitrary. Adjacency map. Doesn't this have something to convert to graphs? No. What's up there? Indentation. Yes. Okay. Well, let's go check out the tests. See if we can find some example. Yeah, something like that. Foo, blah blah blah. Generic. Okay, let's try that. Why don't we try the generic deriving? No, that's not. I haven't written enough arbitrary instances by hand to resort to this. I think I want to understand it better. But that's not going to help us. So, Purescript, QuickCheck, ADT. QuickCheck on custom ADT in Purescript. Prevents it from generating an infinitely recursive structure. You can make generators sized and then resized by -1 each time it is used recursively. An example here. Okay, 1 second. Let's go to here. So, trying to implement the arbitrary instance. This is arith data type, and so you want an arbitrary literal or arbitrary together with an arbitrary addition. And so I suppose using this alternative instance with arbitraries is going to mix and match them somehow. Let's take a look. Arbitrary. There's no real. I mean, so I think we're saying alternative. No, or just alt. No. Maybe it is with gen. Let's go here. Alt gen, yes. So let's see. Alt gen is derived from state. It's a state monad. Encodes a linear congruential generator. Never heard of a congruential generator before. But a state on gen state, which has a size and a seed and a type A. And a seed is what? It's a random seed. And so alt, for some reason, we're supposed to believe that it will correctly it will take the alt instance on states, on the state monad. So let's see what that's like. Given two states, x and y, it will take the input state and it will alt the generated it needs an alt on M. Which would be identity. Won't it? For the regular state monad, not the state monad transformer. Okay, let's not go too deep and let's try to copy what's here. So if I am to believe this, then I would need to do something like having arbitrary empty nodes and then alt that with some arbitrary vertices and alt that with some arbitrary connections and some arbitrary overlays. Where arb_empty will there's a fixed point there. Yeah, that makes sense. And here there's some size, gen resize min5, and then you pass gen resize -1 at each instance. I mean, I get it, I think, generally, but I think it would be nice to add a comment there that would explain things. And so it's not fixed. JSON. gen dot resize -5, gen sized blah. Okay, let's try this. We need to import gen, but it's not from control monad gen. So test QuickCheck gen. So is that the same gen? Might not be. Might not be. Monad gen. Is this supposed to be Purescript? Okay. I think we need to expand our search. Blah 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 fix blah blah blah. Okay, so let's try these things. Maybe we should have the gen elsewhere. I think that's a fairly common thing to do. So I have graph.gen or well here, yeah, it's a .gen. Yeah, I think it makes sense. So new file, gen.pers. And we'll import algebra.graph. And we'll move the instance there and the QuickCheck stuff. So that we can have gen and control.lazy. So then we have a fixed point and we have a G. And it's one of, is that from arbitrary or, oopsie, one of, takes a non-empty array, gen A, selects and executes a random generator for non-empty array of random generators with uniform probability. I don't think that's what we want to do. I'm going to select either a leaf. Right, but it's a fixed point. Yes. Or a V or B. Okay. Yeah, I suppose we can do that. One of empty or import data.empt. empty, or an array with, well, to be honest, this could really just be empty, or vertex, whoopsie, arbitrary. No, it's vertex arbitrary, but it's so let's see. But it's connect. Actually, I think arbitrary, no? And overlay. Prelude. And non-empty also has one off. And oh, off an instance. I see. That's why these things are. Oh well, fine. Not very pleasant, but fine. Might be a lot of things. Might be some things that clash here. We'll see. Okay. Then with graph, yes. P, yes, P. Or G, rather. And still not. Graph with Jen. P1 of blah and blah. It does seem right to me, but I need to make sure I'm using fix from here and one off from here. So same idea here, but why isn't this needed here with size? Well, because it won't blow up the stack, I suppose. But it doesn't mean that it will. They will not try to generate really big things. What's the problem though? Something arbitrary here. Leaf A. Look at this. The leaf. Okay, the leaf is mapped to the arbitrary for some reason. And that doesn't work. Not match and with that graph. So arbitrary expects a gen. Fix takes a function from L to L and expects to return L at some point. So given a graph, we can connect those two graphs. A bit suspect. Yeah, it's the same thing. Is there a time where this was? No, it was still using. It was using lazy, but so let's see. In data Argonauts itself, that's not there. Core, I suppose, is where the arbitrary instance is. No. I suppose it's not there. It's just that generator. I mean, I suspect it's exactly the same thing, but still not great. Okay, let's try this. Say, non-empty array with non-empty array. Yes. Yes, yes, yes. Because I think you want any dot blah, isn't that right? Maybe not. Non-empty arrays are a different thing. So when I use this guy, I'm not using the non-empty array one, but I'd like to. So let's go check non-empty array. The from array. It's just a column. So who wants what? Why does one off want the one off want the non-empty array? Doesn't want. Is there a way to get another one off? We can get the non-empty list one, but the answer is kind of no. And that's fine, that's fine. It's just that this is from non-empty, so we can just use from non-empty, and then we're good. Let's back go build. See if it tells us something about arbitrary here. Whole arbitrary has T0. Okay, let's just try this. You want a gen here. I don't know what the problem would be. You should be able to find an A somehow. So let's try without it for now. See what that tells us. We're trying to match graph of graphs. So you think you have a graph of graphs. But then that's exactly the same error. How about we try the reverse? We try to only have the vertex in it, and then try to work out what that should be. So should that just be vertex arbitrary? No. I mean, is it because empty is problematic because of its lack of type? No. It could even be this. And so how about just empty then? Can you generate one of those? You can't. Okay, I'm a little bit lost here. Should I try with the where clause? Is that going to make a difference? It's a little bit annoying if it does, but let's try. So I think it needs to be that, and E, and the rest past G, where E equals empty, and RG equals this. Yes. Still the same thing. What am I missing here? Graph A, like TA, has leaves and vertices, and okay, well, let's try and write it how it's written here. And here you're telling me that you can match gen with graph. You can match E correctly this time, but I don't know if it makes any difference. Because maybe I mean this should just all be the same, but it's not. This seems to work. So it must be some type annotation shenanigans. That's not great. No type instance was found for arbitrary T1. Okay, so I think it's because we want to constrain things just a tiny bit more here. So we can probably just this was a fairly ambitious quick check. That one, is that one? It's not. It's the one on line 75. This one. Yeah, that should work for like any graph, but that's a little bit crazy. I think I can say like make it like graphs of events, for instance, events, and this makes it like graphs of events as well. Maybe that's enough. Maybe we can't wrap things like that. Let's see. There might be a quick check. Let's do a quick check for with several props. And number of tests that should be ran, seed, pure, result, it's equal, not equal, blah blah. Okay, let's set this one aside. Oh no, really? So now you're failing again. What? Hold on, where is this? Oh wow, yeah, you are. Okay, well, I think I will lay it to rest for now. It's been a bit that we've been battling with this, and yeah, I'll read more on arbitrary instances and figure this out. Clearly there's some problem with either recursion or missing tap annotation here. This is really pretty much exactly what we see here, but it doesn't work. So let's copy this and let's write for ourselves. I think this has been fixed now. Actually, it hasn't, I think. But we're writing arbitrary instance for graph. And this failing test in particular, maybe we actually haven't solved it. So hold on 1 second. Let's see if we can do that. This quick check here, and okay, it builds, and right. So that last one, let's look at it again. Extend extract of P circuit. Okay, well, no, I see that I need to do more thinking about this. We haven't been focused on this, but we will put it back into focus next time. So I'm going to put this like so. Awesome. Good. I'm glad that I'm doing some arbitrary instances for things. That sounds interesting. And yeah, we have quite a bunch of new tests, so that can't be bad, right? All right. Thanks a lot for watching, and I'll see you probably on Thursday. Take care.